Today, I'm excited to have our featured speaker, James Cassidy, a soil expert and senior instructor with Oregon State University, or OSU, in their College of Agricultural Sciences. James is also the founder and faculty advisor for the wildly popular OSU Organic Growers Club. That's OSU's student farm. James comes to us from a non-traditional background, being with the music industry for over 40 years. He's passionate about soil and is very popular with students because of his dynamic speaking style. He's had over 30,000 students participate in the farm's programs. The farm is largely self-supported through produce sales and cultivates over 50 different fruit and vegetable crops. It's just beginning its 25th season. And today, the presentation is designed for IPM managers, so many of you, to understand the fundamentals of soil in order to optimize soil health and prevent insect pests and invasive weeds. So I'll pass it over to you, James. I think your slides look good.
All right. Well, thank you so much. Just hearing that intro, it makes me exhausted just thinking about it. Anyway, hi, my name is James, and as the introduction said, yeah, I teach introductory soil science class in the student farm at OSU. But I want to get right to it because we are short, a little bit of time together. Here we are together at this time in the history of the cosmos, at this particular time in the history of the cosmos, where we can really meet like this, number one, and number two, to actually know some things about soil that people didn't even know 100 years ago by any means. So special time for sure. I really want to talk about what soil is and how it works, specifically for IPM, but generally how it works, I think is very important for anybody who's managing soil. So what soil is essentially, that's made from four different things. It's made from minerals or rocks, how people think of that, and organic matter, those two things. And then it's space, mostly. It's about half of the soil is space. And I happen to have a little soil right
James,
here.
I'm sorry to interrupt you. I'm assuming you've been advancing your slides.
No, I have not.
You have not? Okay, then sorry for interrupting you.
That's part of my gag here. So anyway,
okay.
So
sorry.
I have some soil here. In this jar is some soil, and about half of this is space. Okay, and what soil is essentially it's rotted rock, and it's rock, and different rocks have different minerals in them, and the different colored minerals in here are made from different elements in the Earth's crust. I mean, everything you've ever seen, everything you will see is made from the elements in the periodic table. And that's what's in this rock. And maybe you don't know this, but rocks dissolve in water. And maybe you never imagined such a thing, but they dissolve rather rapidly. And when this rock, which is made out of these different minerals, might have molybdenum, calcium, phosphorus, that's what nutrients are, and that's where nutrients come from. And if you don't believe me that rocks dissolve in water, just take a little bit of table salt, which is sodium chloride, put it on your hand and lick it. And that's a mineral that dissolves very rapidly and release mineral nutrients into your body. And the same thing happens in the soil where rocks dissolve in liquid water on the planet Earth. And every atom inside of your body was once inside of a rock. And then the rock dissolved in water, and that became a nutrient that was taken up by a plant that lived in soil, and those nutrients went into those plants, and then you ate them, or your mom did, and that's why you're here. And that's essentially what the mineral component of soil is rocks that are breaking down into different sizes. As they get smaller and smaller, they become sand, silt, and clay-sized particles. Okay, you got that? But they're made from different kinds of minerals depending on the basic geology that underlies the soils that they form from. Okay. The other thing we have to talk about is this other component, which first of all, it's all about soil, right? But this other component is this organic matter. And what organic matter is stuff that was once alive or is currently alive, but ultimately all this organic matter, like this piece of paper, was once a tree. And trees are made Yes, they're made from some minerals, but I don't know if you know what a tree or a plant is actually made out of mostly. If you remove the water, this piece of paper is mostly made of carbon. And where does the carbon come from to make a tree, to grow a plant, to make flowers, to make food, to make seed, to make roots, to make all that stuff? Where does the carbon come from to make organic matter? Don't have time for questions, really, but I'll tell you, it comes from the atmosphere. Plants, most people think, oh, plants breathe carbon dioxide and they exhale oxygen. No, they don't. Plants don't breathe the atmosphere, they eat the atmosphere. Okay, so plants are actually taking carbon dioxide out of the atmosphere, taking it apart, and then putting it together into wood, into plant tissues. And in order for the plant to take apart carbon dioxide and put it together into these tissues requires energy input to do that. And where does the energy come from to eat the atmosphere for plants? Where does it come from? It comes from the sun. And the sun, 93 million miles away, there's a UV radiation that's coming to this planet, and plants have figured out a way to capture that energy to do work, to take apart carbon dioxide and put it together into wood. And in the carbon-to-carbon bonds that make the wood is the energy of the sun at the time of photosynthesis. And I have just a quick demo. Here's a piece of wood, a tree, right? We made this, and this is mostly carbon from the atmosphere. And if I can get this to 451 degrees, it burns. And that is releasing that energy that came from the sun. So this fire is the energy of the sun that's now being released, and this wood is going back to CO2, and it's releasing energy. And that's what food is. And that's what powers the whole system. Every blink of your eye, every moment that you're experiencing reality is energy that was captured from the sun by plants that lived in soil. Okay, see what I'm saying? It's all about soil. And all the billions, I don't know if you know this, but in a single pinch of soil, there are over 1 billion living organisms. This pinch of soil right now. And they don't even know there's a sun. They eat organic matter. So the answer, if you want to know what the answer is, it doesn't matter what the question is. If you want to know what the answer is add organic matter. That's what you do 3 times a day. That's what powers you, is you're eating organic material. You're either eating vegetables or eating an animal that ate vegetables, but the energy, the carbon came from the atmosphere, the energy came from the sun. So that's essentially what soil is kind of physically. It's made from minerals, different sized particles, sand, silt, and clay, that dissolved and fell out of rocks. And then plants have figured out a way to eat the atmosphere using the energy of the sun, build organic matter tissues that store energy from the sun to feed the billions of organisms in the ground, including plants, including us. The other component is just space. Look at this. Half of soil is space. And that's where the activity in soil is where it is. It's in the space. That's where the air is when soils drain. It's water is stored in small capillary spaces, like this little bit of water between my fingers right now is being stored there against the force of gravity. And small pores hold water against the force of gravity, and large pores drain under the force of gravity. So soil is half of its space. And that's where the activity in soil is. That's where the bugs are, that's where the roots are, that's where the air is, that's where the water is. And the mineral component is what's dissolving out to release the nutrients. And then the nutrients are being taken up by the plants using the energy of the sun and the carbon of the atmosphere to lock those nutrients into the tissues. And just really briefly, I promise I'll move on here, but when I burn this, think about a fire in a fireplace. You keep adding wood and adding wood and adding wood. And you get all that heat and that energy, that light, and the wood disappears. And where does the wood go to? It goes back to CO2. And what's left over in the fireplace in the morning after the fire is out? Ash. And what is ash? Ash is the mineral component that was taken up at the roots of the plant. And that's how a plant works. So kind of a brief, very brief and quick overview of what nutrients are, where they come from, what soil is, what organic matter is, and that soil is half of it is space. And it's this where the activity in soils happens. Now, maybe you don't know this, and I'd mentioned there's over a living organisms in a single pinch of soil. And it's not just a billion of one thing. It's literally tens of thousands of different species are in this pinch of soil right now. And what are they doing? They're cycling carbon, energy, and mineral nutrients. That's what they're doing, is they're using the dead stuff to power the system. It's almost like, now get your head around this. You ready for this? It's almost like we live in a giant solar system. You know what I'm saying? We do. It's all being driven by the energy from the sun. Every blink of your eye, every moment of reality that you're experiencing is energy that was captured from the sun by plants that live in soil. Now, maybe there's something you don't know, maybe you do, but there's over 20,000 different named soils. Write that down, 20,000 different named soils. We call them soil series. Just like plants and animals, there's lots of different names for all the different plants and animals, similarly to soil, because there's different types of rocks and different climates and different organic matter being produced in different places. And all of those things make every soil a little different. But of those 20,000 different soils, they all belong to one of the 12 soil orders. So it's a higher level organization, are soil order. And if you look at this image here on the left, we have a soil order of which there's probably thousands of different kinds of iridosols. And this is what you're looking at is if you dug a hole and looked at the wall of soil, and you can see that it's organized into horizons, these layers, right? But here, an iridosol means it's arid. And where it's arid, there's not much water. And when there's not water, there's not much dissolution of mineral nutrients. So there's not a lot of fertility being given off. And so the soils are very thin because it's just that the water is eating down into the rock. And look here, if you look at this image, right here, you can see this layer. That's a layer of salt because it rains in the desert a little bit, just enough for water to trickle down with some salt in it. And then it stops raining, and over 10,000s of years, you get this layer of salt. And so you have a very low amount of organic matter here because it's not a lot of nutrients, because there's not a lot of water. And that's what an iridosol is. And this is the kind of plants that live there. And that's what a native plant is. A native plant is a plant that is not only adapted to the climate, but to the below ground ecosystem called soil, which is in this case very salty, very low energy because it doesn't have a lot of organic matter and not a lot of nutrients. And these plants have figured out a way to live there. We're here on the right hand side, we have what's called a mollisol. And a mollisol, of which there's thousands of different kinds, or hundreds for sure. This is this is in feet, down to 2 feet. You see how dark it is? And the reason this soil is dark is because it has a lot of organic matter in it because of roots that have grown there, lived and died, and left behind carbon and energy. And there's a lot of bacteria in here that are cycling carbon, energy, and mineral nutrients. And this is the most important agricultural soil in the world. And it's the reason that we're a superpower, because we have more mollisols than any other country in the world. And if you look at a map of the global soil regions, here you can see mollisols represented here by green, right? Look, the United States, 21% of the United States is in mollisols. And worldwide, that's only 7%. And there's only one other nation in the world that has as much mollusols as we do, and that would be Russia. That's what the Cold War was all about. They who have the advanced agriculture have the advanced technologies to have Zoom meetings or whatever, or Teams meetings, because the technologies are driven by innovation that was based on agriculture, and the wealth that comes from the land allows everybody to become a specialist. And don't get me started. But this what you're looking at here is a map of political power, and it's powered by the sun, because of some soils can capture more energy from the sun and capture more and take apart more carbon dioxide to make food, which can be traded for money, which can allow for innovation and for everyone you to become an expert at what you do. So, and I'd love to talk to you more about this, but we got to keep moving. Here, just show you, here's an oxisol. This is the tropical soils. They're mostly just rust. Here on the Oregon coast, we have something called spotisols, and these are sand soils that form from sand dunes. Very different set of circumstances lead to a very different soil environment and special plants that live on the Oregon coast. There's something called an entisol, and an entisol is a very young soil or a very cold soil or a very dry soil, so it hasn't really developed much. And in fact, this one is called a typic quartz samand, and it's an entisol. And its samand means sand. It's just a quartz sand, and in quartz sand doesn't have a lot of nutrients, so there's not a lot of development there. So a different kind of soil formed from the sand than it would from other kinds of rocks or minerals. Here's an inceptisol. This is one from Georgia. It's called Georgia, and it's just one. Georgia is just one of the 20,000 different named soils. So what I want you to understand is that soil doesn't come in a bag. Soil forms over time when there's some moisture and rocks dissolve in water, and those nutrients get taken up by plants, are powered by the energy of the sun and carbon from the atmosphere, and then the roots themselves shape the soil and improve the soil's structure so that water can penetrate deeper. And the plants that were successful at improving the soil were more likely to succeed and pass on that genetic information. And their offspring improved the soil. So plants over millions of years, hundreds of millions of years, have been influencing the soil. And in fact, plants themselves are a soil forming factor. So kind of a big picture view there. And so I kind of want to pull up for a second, and we just have to talk about the functions of soil. And I know you know this, but some of them are actually quite important for IPM. Just quickly, obviously, soil is a medium for plant growth, but it is a recycler of nutrients and waste. It also takes in carbon dioxide, right? And oxygen comes out, and carbon is fixed in it. It's a habitat for the billions of organisms in a single pinch. It also controls the flow and purity of water. As water moves through soil, it is physically, chemically, and biologically filtered. You might understand why that might be important for a class like this. It's also an engineering medium. I mean, the building that you're sitting in right now is sitting on top of soil, and soil scientists and engineers figured out the properties of those soils. And soils are different in different places. So everything, it's a lot of engineering information you have to know where you can build a 10-story, let alone a 100-story building. But what I wanted to focus on were these three functions. And I'm sure it's quite obvious to you now why this would be important. Starting with the control and flow and purity of water. When you're using pesticides or herbicides or other chemical controls, the rate at which the water moves through the soil determines how long it takes before it gets to a contamination of groundwater or surface waters. So slowing the water down gives it time to become filtered physically, chemically, and biologically. So just generally, we'll talk about it a little more. And also, it's a recycler of nutrients and waste. And whatever you're putting on as a chemical control, or whether it's biological controls or whatever, but all of that is they're just chemicals. And in the billions in a single pinch in soil, there is an enzyme to take apart almost every compound with the exception of what we call forever chemicals. But because what is a chemical? It's made from minerals and it has energy in the carbon to carbon bonds, and there's a bug that can take it apart. Where is all the dead stuff? When things die, they get decomposed by the soil, and then they're released again as nutrients to be taken up. I mean, every atom in your body was once in a rock, yes, but it's been recycled billions of times through the soil system. And that's what it's all about, is this recycling of nutrients and waste. And waste, whatever that means, that's just a term we call things that we don't want, but ultimately they all are recycled. And of course, most importantly, it's a habitat for soil organisms. Who's doing the recycling of the nutrients and the waste? Habitat for organisms are billions in a single pinch below ground. And of course, plants are driving the whole system because they're pumping solar energy in the form of ATP into this whole system. So the entire system is driven by solar energy, and rocks dissolve in water, which are nutrients. Plants fix those nitrogen, all those nutrients into their tissues, and carbon from the atmosphere, energy from the sun, and they grow, and then they die and they decompose, and all of that is recycled in the soil by organisms that live in the soil below the surface and release them. And that is what happens. And then, of course, soil physically and chemically and biologically controls the flow and purity of water. It's a super important concept. So that's kind of where I wanted to get to, just as an introduction. And I do want to talk about these soil physical properties. I've already shown them here. We're not going to focus on all of these, but the different types of soils that form from different kinds of geology under different soil forming conditions with different organisms present, different native plants, etc., are governed by soil physical properties. I mean, the physical properties of soil determine what the soil can be used for, what kinds of life it can support, etc. And I really want to focus briefly on color, texture, and structure. Okay, and because different soils, if you just start noticing, you should dig a hole wherever you go to do some work. Before you do, just dig a little hole and see what is going on below ground. And you'll notice that there's different colors. And I'm just going to briefly focus on color just for a moment. And color, when you look at a soil and you look at and the deeper you go, it changes color as you go. And it tells you information. The amount of organic matter can be indicated by color, and the types of oxides that are present hint at the general hydrology, how wet or cold or dry is the soil over time. And you can tell the amount of moisture or the moisture regime. How often does it rain? And what type of rainfall? And it also hints at mineralogy based on the colors of the different minerals that are present. So there's a system called the Munsell color system. It's just a book. And all you have to do is take a piece of soil and match it to the color of these chips on this page. And in the Munsell color system, by simply matching the color of the soil to this chip, we get 3 pieces of information. We get the hue, the value, and the chroma of that soil. So by simply matching the soil to these colors, we get 3 pieces of information. And those 3 pieces of information tell us the mineralogical composition, the amount of organic matter, or how wet the soil is, because when soil gets wet, it gets darker, right? But you can measure that used by simply matching a chip. And it's an indication of the hydrologic regime. How often is it wet and for how long is indicated by this thing called chroma. And it's the amount of pigment. Can you see down here on this chroma scale? It goes from very, very low chroma, meaning not lots of pigment, to very high chroma. And as it turns out, the soil's color, if it's on this end of this color, that tells you that it's wet all the time, and it's probably cold, and it's probably anaerobic. And oxygen is super important for the decomposition of compounds that may be entering the soil. So a color that looks like this, a soil that's dark, kind of this clay color, we call it, or gray, right, is a soil that doesn't drain very fast at all. And it can hold lots of moisture, but it stays cold. It doesn't have a lot of oxygen. So the organisms that live there are anaerobic, and they're very slow at decomposing any compounds that might be entering, i.e. chemicals that you may or may not be using as pest management or herbicides. So it's just a really just fast, but really knowing the color of the soil tells you that information. And you can look it up and you can learn more about it. And I'm going to show you some apps at the end of the talk that get into detail how we do that. So I do want to switch to texture, because texture is the percent sand, silt, and clay. And sand is just a large particle, silt is a small particle, and clay is a super small particle. And the different size and proportions of sand, silt, and clay determine how much water can be held, what is the infiltration, how fast does water go through it, the nutrient supply, the aeration, the temperature, the drainage, the oxygenation. Sandy soils, and you all know this, drain fast. And when they drain, they pull in oxygen, but they don't hold that much water. Where clayey soils slowly have water move in, but stay wet and don't have a lot of oxygen in, and they can be pretty cold. And that's really different. And that's all based on the texture, the percent sand, silt, clay. And soil texture, by definition, is the percent sand, silt, and clay. And it doesn't include the organic matter or coarse fragments, which are anything larger than 2 millimeters. So these different particle size classes are, they're designated by the USDA. They're just man-made concepts, of course. Sand is anything from 2 millimeters down to 0.05 millimeters. Silt is anything from 0.05 millimeters down to 0.002 millimeters. And anything smaller than 0.002 millimeters is called clay-sized particles, okay? And you can evaluate the amount of sand, silt, and clay in the laboratory, but you can also learn how to do it using your hand. And some of you probably know this. Just by handling the soil, the amount that you can sculpt it, the more sculptable it is, the more clay there is. That's why they make sculptures out of clay, right? And bricks and everything. And the grittier it feels, the more sand there is. And siltiness can be felt by how smooth it is. And these are all techniques that you can learn to do in the field. But there's an app for that. So just want you to know what texture is, okay? And so, for instance, if we have a soil, and they all have to add up to 100%, right? That is 60% sand, 25% silt, and 25% clay and 15% silt. What we have is a textural class called a sandy clay loam. And you'll see there's 12 different textural classes of the soil. And clayey soils on the top half here hold a lot more water, don't drain very fast, don't have a lot of oxygen, can be very anaerobic, and it can be kind of cold. And there's a whole type of plants and animals that are adapted to those conditions. Where really sandy soils, like loamy sands and sandy loams and even sandy clay loams to a certain extent, they drain pretty fast. And what loam is approximately equal parts sand, silt, and clay. And that's good. And that's why loams are good for agricultural purposes, because they hold a lot of water, but they also drain. And what do plants need at their roots? They need air and water at their roots, because plants breathe oxygen at their roots. And the billions in a single pinch breathe oxygen down there to do biological functioning, to increase the rate of turnover of carbon, energy, and mineral nutrients. So a loam is like in that pie graph, it means about half of those pores are large enough that they're filled with air, and half of them are small enough that they're filled with water. And that's an ideal kind of texture for agricultural purposes, but not for wetland plants and not for desert plants. You see what I mean? But for agricultural purposes, you got to know that stuff. So I wanted to show you this image of a cucumber plant that is sick. And you know, it's how I said soil textures, percent sand, silt, clay, not including the organic matter, anything larger than 2 millimeters, coarse fragments. Coarse fragments matter because when you apply an herbicide, in this case an herbicide, you look at the directions and it says, oh, you have this textured soil, put this amount on. But if you're not accounting for the coarse fragments in the soil reduce the soil volume. So this particular farmer who actually asked me to help him figure out what was going on was applying his herbicide according to the directions based on the texture of the soil. But he didn't account for that half of the soil was occupied by big rocks. So in a sense, in fact, he over applied the herbicide, even though he was following the directions, because he didn't think about coarse fragments in the soil. And here's an image of a soil that has a lot of coarse, what we call coarse fragments, which are just large rocks. But think how little volume soil there really is in between these rocks. And if you didn't account for that volume loss and you applied an herbicide or a pesticide or something based on the texture of the soil, it didn't account for that. You can see how that's a problem. So that's just an example, and just one example of how important this information is for any land manager. So what texture relates to is all of these things: the surface area, the pore volume, the pore size, the nutrient supply capacity, plasticity, cohesion, drainage rate, aeration, temperature, all that stuff is related to texture, which is the percent sand, silt, clay. And I really want to draw your attention to this idea of pore volume, the space in the soil, right? Larger amounts of total pore volume mean more habitat for organisms, roots, air, and water. And then pore size is related to the size of the particles. So real briefly, pore size is positively correlated with particle size. And that's because sand is a large particle. And so large particles have large pores in between them. And so sandy soils have large pores, right? And so they drain under the force of gravity because large pores drain under the force of gravity. And very, very small particles like clay, less than 0.002 millimeters, have very, very small pores. And you might notice that the shape of the particle of clay is very different too. Even though it's really small and you've never seen it, it's a tiny little plate and it randomly stacks up. And it has a very small pores are related. So again, particle size and pore size are positively related to each other. Where pore volume, the total pore volume is actually much higher in clays, even though the pore size is very high in sand. I know that's an awful lot for you to get your head around here in 18 minutes or whatever we've been talking so far, but it matters. And that's because you'll see here that so sandy soils have large pore size, but relatively small pore volume because of the shape of the particle. They're spheres mostly. And look how fast water can infiltrate into sandy soils. Within an hour, it's down to 4 feet deep of just a flood irrigation. Where in a clayey soil that have very small pores, that infiltration takes a long time. It takes 4 hours just to get to 2 feet deep. And you can see that's a really big difference. And if you're interested or concerned about the transport of chemicals or manure or whatever, the different soil texture can make a real big difference into how it moves in the soil and how quickly. And a sandy soil drains faster, so more oxygen comes in. And the billions in a single pinch can process those chemicals or that manure. Whereas clayey soils tend to hold things and they're colder and they're anaerobic. And just a real brief understanding. I just want you to comprehend how important, I'm sure you're already doing it in your mind, how big a difference these different textures of soils make in how the ultimate fate of any sort of treatments, etc. So, just this should be pretty obvious by now. The water holding capacity of sand is low, where it's very high in clay. The aeration in sand is very good, I guess, or high, where in clay it's quite poor. Drainage is rapid in sandy soils and very slow in clay. And the nutrient retention, as we're going to get to in a minute, is very low in sand and very high in clay, because clay is a different thing. Of course, silt is somewhere in between. Clay is a different thing. And we're going to do a deep dive on clay really soon here. So I just wanted to get to understand what texture is. And then there's this thing called structure, and we'll kind of be brief on this as well, because we just don't have that much time. So what texture is the percent sand, silt, and clay, not including organic matter or coarse fragments, where structure is the spatial arrangement of those particles, which is kind of a really different concept, okay? And it's how they're arranged. And you can see here, here's some aggregates that are made of very small particles, and they have tiny little pores on the inside, but these are clusters of soil, and that's what structure is. And look at the large pores between the aggregates and the small pores inside of the aggregates. So here's a soil that is well structured, that has a lot of oxygen in the large pores, and it stores a lot of water and nutrients in the small pores, and it drains, and it has deep infiltration. And this is a soil that has a wide pore size distribution, as opposed to this very sandy soil, which has about the same amount of large pores as this soil over here, but these are just grains of sand. So there's no small pores to store water. That's a narrow pore size distribution. You can imagine the difference that makes to a plant, and the types of applications that you might do to help with pest management generally. Completely different habitats for the billions in a single pinch, and yet they're there in both types. And look here, so just like here is a soil that has infiltration. You put some water on it based on the average pore size, and it only goes down a certain depth, but you can see how roots actually enhance the infiltration because they make larger pores that are connected. Even after they die, even after they decompose, roots leave behind a casting of their former connected self, which allows for deeper infiltration. And plants improve the infiltration of soil even after they're dead and even after they completely decompose for the next generation of plants. And that happens over and over and over again, which improves the soil, adds more carbon, adds more energy, has the water go deeper. The roots can go deeper, the plants can get bigger. There's more additions of organic matter over time. And that's what soil building is. That's what soil health is. That's why soils work, is because plants have improved them so that they can get more carbon and energy into the system, which feeds the billions in a single pinch, which release more nutrients, which allow for more plants, which allows for more sunlight capture in the form of carbon-to-carbon bonds and more harvesting of carbon from the atmosphere. Man, that's a lot for 10:30 in the morning. Hope you're up for it. So now I want to move on to, that's kind of like physical properties, but I want to talk about the chemical properties of soil. And this, I think, is extremely important for IPM. So pay attention to this. So we know what soil is, right? It's rotted rock, and here's a rock, right? And rocks are made out of minerals. And the different minerals have different colors, right? And those different colors are essentially, this is a map of nutrients that's locked up in a rock. And that dissolves in water. And when it dissolves, those particles fall out as different size particles, sand, silt, and clay size particles. Sand is just a crystal that dissolved out of a rock of a certain size, but it's just a rock. Silt is just a smaller rock, but clay is a tiny, tiny thing that forms when rocks dissolve and then recrystallize at the surface, at normal surface temperatures and normal surface pressures, and is the product of dissolution and recrystallization at the surface. And they're tiny, and they have a giant surface area. So rocks, they dissolve in water, and when they dissolve out, look what dissolves out of them. Nutrients, right? And some of these elements that dissolve out of rocks actually recrystallize. And when they recrystallize, they form these sheets of silica and aluminum oxide that can only get to 0.002 millimeters before they fall apart. And that's why the size class of clay, it's a secondary mineral that is forming in the soil that can only get to 0.002 millimeters. Okay, you ready? We're going in now. When rocks dissolve, the most abundant elements in the Earth's crust are silica, oxygen, aluminum, and iron. And that's mostly what rocks are made out of. And when they dissolve, they form these little building blocks of the crystal called clay. Silica has a certain size and a certain charge that forms 4 covalent bonds with 4 oxygens to form a silica tetrahedron. Aluminum has a certain size and a certain charge to form 6 covalent bonds with oxygens. And these oxygens can be shared, and that's what the crystal forms from. Here you can see the silica tetrahedral sheet, and here's the aluminum octahedral sheet and a silica tetrahedral sheet. And this is called the layer. And the layer, there's one and another and another and another, and they stack up by the millions, if not trillions. And they can only get to about 0.002 millimeters before they fall apart. And as it turns out, there are other elements that are dissolving in some rocks. Some rocks are high in iron, and others are high in magnesium, or both. And as it turns out, iron can substitute in for the silica tetrahedron, and magnesium can substitute in for aluminum. And remember how I said these have almost the same size and almost the same charge, but not quite. And a little bit of negative charge is left over. I know, but it's like, what is he talking about? Hang on. When iron is substituted into the tetrahedral sheet, there's a little bit of leftover charge. A negative charge is on the surface of this little crystal. Similarly, when magnesium substitutes in at the time of creation of this crystal in the octahedral sheet, we end up with a net negative charge. Okay, listen now. Rocks don't have negative charges. Sand doesn't have a negative charge. Silt doesn't have a negative charge, even though they're small. Clay is a different thing. It has a negative charge on it, and that negative charge is where the nutrients are stored in soil. What sticks to negatively charged? This is an electrostatic charge that is propagated to the crystal surface. And a negative charge, what sticks to negatively charged things? Positively charged things, like most mineral nutrients, calcium, phosphorus, potassium. So all those things that we put on as fertilizer are positively charged ions that stick to the negative exchange complex on clay. And that's how soils store nutrients for plants. And this has a very big implication for IPM specifically. I'll show you in a moment. Here's clay at 100,000 times magnification, 100,000 times magnification. And it has net negative charges all over it due to isomorphic substitution on the secondary mineral called clay as it formed. And what sticks to that? Positively charged nutrients. But here's the slide I really wanted to get to. Look, here's clay. You can sort of see it now. Here's this tetrahedral sheet, the octahedral sheet. It's got all sorts of substitution in it. Look, calcium is stuck there. Every calcium ion in your skeleton, in your body right now, was dissolved out of a rock, and it was stuck to the negative exchange complex of clay. And the plants come along and they can remove it. And that's how it got into you, because you ate those plants. But what I really wanted to draw your attention to, here's some other look, these are other fertilizers, right? Potassium, calcium, magnesium. But what this image shows, look, see this thing right here? This is 2,4-D. 4-D, as you know, is an herbicide, and it has a charge on it, and it can be stuck to clay. So is once it's stuck to clay, it loses its efficacy because it's attached to something. And so it's no longer, it minimizes its ability to do what it was intended to do. And look at this carbon double bond carbon ring here. Lots of carbon and lots of energy in there. And you know what? There's a bacteria or a fungi that will break these bonds and disassemble. And that's what we talk about, the recycling or the cleansing biologically. So this is chemically holding this 2,4-D, and then it biologically, because it's held there, as long as there's water and oxygen, that those bugs can eat it. And so for almost all of these chemicals, if they can be held in the soil long enough, they will then be biologically biodegraded. And that's how soils, they physically filter these things out, they chemically filter these things out, and then they biologically take them apart, disassemble them, and they just go back into the soil and are used over and over and over again. However, in sandy soils, we don't have, this process is greatly reduced because there's no negative charge. And they're also, the drainage is very rapid, so these chemicals can move very rapidly and get into groundwater. See how that works? I hope you do. So, as it turns out, not only clay does that, but organic matter itself, organic matter has a net negative charge on it. And this is what it looks like. I'll show you, hopefully this will come up pretty quick. Here, what organic matter is, ultimately, the ultimate fate of organic matter as it's stored in soil is a random molecule. And it's a random molecule that has a giant surface area and it has net negative charges all over it. It performs the very same function as clay, except it's easy to control organic matter. You can increase the amount of organic matter in the soil by growing cover crops, by adding compost, by minimizing losses of organic matter, by leaving mowing clippings, all that, minimizing disturbance, keeping the oxygen away from it so it doesn't burn off, because it burns off biologically. The exact same process that happens in a fire is happening in your gut right now, is happening in the soil, because the bugs are oozing out enzymes that lower the activation energy necessary for the oxidation chemical reaction called burning to happen. So you can increase the cation exchange, you can increase the amount of negative charges in your soil by adding organic matter, building soil health. That's what soil health is. And what is organic matter made out of? Carbon from the atmosphere, energy from the sun that powers the whole thing, that increases the biological activity, the bugs in a single pinch, which allows for the more rapid turnover and the more degradation and recycling of nutrients. That's what soil building is. And that's how IPM is integrated into that. We try and do everything else we can first using beneficial organisms. I mean, soil is a beneficial organism. It's billions of them, so, and then we're trying to do what we can before the big guns come out. But even when we do use chemical controls, we need to know what kind of soil we have to see if it's a higher risk environment or a lower risk environment. I hope that makes sense. So very briefly, here's how a plant works, okay? A plant eats the atmosphere and it takes apart carbon dioxide to build carbon-to-carbon bonds using the energy of the sun. That process releases oxygen. Plants also evaporate water at their leaves because they're high surface area, which lowers the pressure of the water inside relative to the water stored in the soil. So water is sucked into the plant because of evapotranspiration. The minerals and nutrients are dissolved in the water and go into the plant and are part of the plant. What you may or may not remember is that plants breathe oxygen at their roots for the same reason you do, to break apart oxygen, to put on the mitochondria, the oxygen is on one side and the energy from the sun is on the other side, which goes through the electron transport chain that allows for creation of ATP and all that jazz. And then they exhale CO2 at their roots, just like you do, just like you do. Right now, every breath you take is oxygen in, CO2, water vapor, heat out. Oxygen in. This is what you're doing. You eat food, you add oxygen, it burns at a low temperature because inside of your gut are microbes that lower the activation energy necessary to break apart, to burn, and then you exhale. You can feel the heat, you can see the water vapor, and the CO2 is leaving. And that's what's happening. You're doing it with every breath, and plants do the same thing. Getting down to one of the last slides, I really want to show this to you, how a plant actually gets nutrients. And look, here is a tiny soil particle, and here's a root hair, right, of a plant. And look, soil has a negative charge on it due to the substitution on the crystals of the secondary mineral called clay, but also organic matter has a negative charge. And look what's stuck to it, mineral nutrients. But also other things are stuck to it, as we've discussed. You know, chemicals can be stuck to this negatively charged particle in the soil. And look, here's the CO2 is exhaling from the root. CO2 dissolves in water, and these nutrients are stored here electrostatically. They don't wash away. Even when you water the ground, they're stuck there. But plants can get those nutrients because when they exhale, the CO2 dissolves in the water, which forms carbonic acid. And carbonic acid, like in a soda, when you open a can of soda, you know how it tastes sort of lemony fresh? That's because it's forming carbonic acid, which further dissociates into hydrogen ion. And that's what acidity is. And that's why a can of Coke tastes like it's very acidic. And that hydrogen ion is more strongly adsorbed to the negative charge than the nutrients are because it's so small. So 2 hydrogen ions are more strongly absorbed to this negative charge here than this calcium is, and they actually kick it off. So the acidification at the roots from exhaling CO2 actually makes the nutrients fall off of the soil particle, but in close proximity to where the water is being sucked in because of evapotranspiration. And that's how calcium gets into the root and becomes part of the plant. And then you eat it. And then inside of your gut, there's a gut microbiome that oozes out enzymes that dissolves it. And every calcium ion in your body was transported to make the skeleton inside of you. And when this plant dies, the same thing happens. It goes into the soil where there's a microbiome there that dissolves the organic matter, releases the carbon, energy, and mineral nutrients, and it's recycled. Those nutrients are then recycled back on soil for the next generation of plants. And note that look at the pore structure left behind by this plant. Eventually that will all rot away, and now you have a big pore, a medium pore, and a tiny pore. And plants over time improve the soil structure of the plant. That's why you want to minimize disturbance to improve soil health. Now, you can't eliminate it, but you can minimize it as long as you know what kind of soil you have. Some are more resilient than others. Clayey soils are slightly more resilient in some ways, but not in other ways. Sandy soils are quite resilient, but if you turn them too much, you get oxygen in and you lose organic matter. So it's an awful lot. And no, if you get nothing else out of this talk, I hope that you get that soil is habitat. And once you understand that soil is habitat that is doing these functions, that you will try and improve the habitat by doing things that improve soil quality. I'm not going to give you the list of what those things are. You can look that up. But it's essentially just minimizing disturbance, maintaining levels of organic matter, increasing the amount of organic matter as best you can, because that's the energy from the sun that powers the whole system. I mean, look here. Here's the biology. Soil is a living thing. Look, there's a little ocean of water between 3 pieces of sand here, and there's an entire ecosystem here in between 3 pieces of sand. And this sand is dissolving mineral nutrients into this water. Up here is a root roots give off carbon and energy to feed the system. Roots 10% of the photosynthetic production of plants is literally being leaking out to feed the biota. And why would a plant do that? Because the biota is dissolving organic matter and releasing nutrients. It's a symbiotic relationship. That's how soil works. It's a living thing. And soil is a physical, chemical, and biological filter. And that's what as long as you understand those basic things, you can look up the rest of it. You can figure the rest of that stuff out. And what is that you can actually use these exciting web-based tools to just go to a site and look up these physical and biological, mostly physical properties. And there's a couple of ways to do that. And some of you are probably familiar with this. There's the Natural Resource Conservation Service Web Soil Survey, where you can make a custom soil map for your management area. Now, this requires some skills. It's not super easy to use, but it's extremely powerful. And if you just go to the Soil Web Survey, I'll show you in a second, there's a tutorial and you can learn how to do it. But you really need to do that. If you're in charge of some city park, you need to have at least a soils map and some understanding, because all that data has been collected over the last 150 years. The Soil Conservation Service started after the Dust Bowl. They went out and they mapped all the soils. I don't know if you know that, but they mapped all the soils in the country, or most of them. And that data is available for free to you. And there's also this California Soil Resource Laboratory, which is a very fast and easy use of the same data, but it's been kind of streamlined for use for professionals and for or just for the public. And there's also an app for that on your phone. And it's like, dang, is this guy going to bring out his phone? And I'm going to show it to you in just a second. So what I'd like to switch to, and I hope this is going to work, I'd like to switch to the view of my browser. If someone could confirm that they're actually seeing that, that would be great. Yeah?
Seeing it.
Yeah, great. But here's the Soil Web Survey. And you go to the Soil Web Survey, and I'm not going to, like I said, I'm not going to spend a huge amount of time on this just because we kind of have a slow connection because of Teams. But here it is, and you just start with this button right here. And there's a whole tutorial on how to use it and the basic steps, how to get an area of interest and make a soil map and look for different attributes, the cation exchange capacity, the amount of type of clay, and all that stuff can be mapped. And I'm not, like I said, I'm not going to do an extensive thing. I'd love to show you in greater detail how it works. But essentially, you navigate to some place and you just put in an address. And once you put in that address, it'll take you there, and then you can make a soil map from it. And it seems like we're going, it's a little too slow. I think we have a little bit of time, don't we? How are we doing? We got another 15 minutes or something, I guess. And you just go to this, and I can put in, say, my address. If you want to send me a pizza, here you go, 205 Southwest 2nd Street, Corvallis, lovely place, Oregon, 97333. And I hit view, and now it's going to take me to where we are, and I live right up by the river here. And then I go to this area of interest tool, and I say, hey, I'm interested in this area, includes the waterfront, etc. And now it's creating the area of interest, and from that, it's multiple areas of interest, whatever. I'm going to make a soil map, and it will tell me the soils that are here and make a map. And there's a whole bunch of them, even in that little area. It's only that's only 139 acres in that area of interest. And there's Amity, Silt Loam, Chehalis, Willamette, Woodburn. And if you click on one of these, it tells you the type of soil that is. And you can make more detailed investigations, and it's very, very incredible. Really, look at the texture. Silt loam, silt loam. Now you know what that means, and it gets clayier as you go down. So a silt loam is an equal parts sand, silt, clay, but it has a little more silt in it. So it has good medium drainage, but it has a good water storage, And down here, it has high cation exchange capacity, and so it can store nutrients further down, on and on and on. So that's one real powerful tool that you can make a custom survey, get it as a printable version or as a PDF, as a printable version or as an electronic version. You could share it. You can explore different attributes in the soil, like how about here's soil properties and qualities, things specifically like the type of clay. Here's soil health properties, like the percent organic matter. We can make a map of this percent organic matter simply just by clicking on that, and we'll view the rating. And here it makes a map of that. You can see this map right now. Maybe you can see it, and it shows a map of so that probably this is lower soil health than this, and it actually gives a description of those different things, etc. So that's really powerful. Similarly is the California Soil Resource Lab, and this actually is some grad students took the NRCS data and made it more accessible to just regular folks. And it's this Soil Web apps, and you go to Soil Web and you accept whatever they're asking you to do, and you can, I could navigate to some location, like, I don't know, how about my dad's house? He's passed away, but 584 Inca Lane, New Brighton, Minnesota 551. I think that'll work. No results because I spelled it wrong. God, it's kind of annoying. New Brighton, Inca. And you can do this right now. Look at those different soil types. Are already, these lines indicate different soil types. So in this one where my dad's house was, is a soil called, well, Hayden. And look at the percent organic matter. Here is a graph of it. Here's the percent sand at depth. It's pretty sandy, 60% sand, a little less down below. Here is the pH of that soil. It's somewhere about 6.5. It goes up to 8 when you get down to 140 centimeters. Here's the cation exchange capacity, the amount of charge on the soil. Here's the percent organic matter. Here's the percent clay. You see how that works? So you can, and there's this app works, and that's just the beginning. That's just soil properties. Here's the hydrologic and erosion ratings and the soil suitability ratings for urban land, for irrigation and engineering and wildlife, you know. And that's, you can just explore this, and it's very easy to use, okay? And what's really cool about this is that there's an app for your phone that does the same thing, and it does it wherever you are. So, for instance, I don't know if you can see me, and a guy on a Teams meeting brings out his cell phone, but there's an app called Soil Web, and I can get my location, and it's the same NRCS data for this location right now, and it's getting my location data, and it's going to tell me what's underneath the building where I live right here, and it's a soil called Willamette. I don't know if you can see that. It's probably not that great, but we had seen it before. And I can actually click on that, and I can learn. There's a description of the soil and all the horizons, and I can actually look at the same details that we were looking at before. And at minimum, this is free. Okay, this is 150 years of data collected by the United States government to serve the people, and it's free to you. And that is called public investment that has allowed us to become one of the richest nations in the world. And it's because of agriculture. And it's because of soil. So you should all right now get on your cell phone and see if you can get the Soil Web app. I don't think it's been updated for Android in recent history. I know there's been some problems with that. But if you have an iPhone, but even if you don't have an iPhone, here is the same information using Soil Web from UC Davis, using the NRCS information. So I have just one more thing I wanted to show you. Well, a couple things here. And then we can go to kind of a question and answer session. And I just wanted to show you this slide. I hope it comes up. This is a really cool slide. It kind of captures everything we've been talking about. This whole thing, this whole existence of being on the planet Earth is being driven by solar energy. And it's being, and the ability for this rocks to dissolve, the fact that we have liquid water dissolves rocks, which allows them to be reconstituted by genetic information, which the genetic information that's stored in every cell in your body itself is made from dissolved minerals. Get your head around that. The information stored genetically in you is being stored on a double helix, which is made out of dissolved minerals itself. And these are the right here below ground under this plant. These are the macronutrients, and here's the micronutrients. And that's what it takes to build these tissues and to do all these functions. And the carbon is coming from the atmosphere, and the energy is driving this whole system. And you can see, look at all this stuff, like potassium is really important for fruit quality or seed quality. Sulfur is important for quickening maturity of fruits. Improving winter hardiness is phosphorus. And you can see that all these nutrients have functions in a plant, and they've been selected for over millions of years to become better plants that, look at the rooting system of this thing. It's shaping, it's sculpting the soil to have better infiltration. And what is a root after death? It's organic matter. It leaves behind carbon, energy, and mineral nutrients. And when it gets biodegraded by the billions of single pinch, now it has deeper infiltration. And the next generation of plants can recolonize those root channels. And that's what this thing called soil is. It's a self-organizing. It self-organizes over time, driven by genetic information and energy from the sun and carbon from the atmosphere. And all these functions that are in these plants, we eat plants, or we eat animals that ate plants. And all of these things have this similar, many of the same functions in us, because we're all related. And that's what the mineral nutrients are doing inside of us. I mean, we're mostly made out of water, we're mostly made out of carbon, but just like a plant, mostly made out of water, mostly made out of carbon, with a little bit of ash in it. And when we die, we can be cremated, we become ash. And what is ash? It's the mineral nutrients that are inside of us. Or we are buried, and when we are decomposed, we are recycled, because it's one of the functions of soil, is the recycling of minerals and nutrients and waste. And all those nutrients, what happens to them? They get stuck on the negative exchange complex of clay and organic matter, and they're stored there at the surface of the soil. In a mollisol, more of them are stored. And a mollisol has more organic matter, more carbon, more energy, more mineral nutrients at depth. And grassland soils, and that's what we have in the Midwest of the United States, and that's where the agricultural economies were based on that. And we have more of that kind of soil than anywhere in the world. And that's why, for good or for bad, we're running the world, you know? And then it all comes around. It's like the circle of life, man. You know what I'm talking about? And you're very, very involved in that. I'm so excited to be talking to people who are managing the landscapes for the use of people, and concerned about soil health and how to manage pests in a way that's responsible to the soil. And I hope you got just a little bit of that in my presentation here today. And I know we're pretty much out of time, but I want to make one pitch to you. You know, I run the student farm. I've been doing that for 25 years as a volunteer. 30,000 students have gone through this program. They've learned this in my classes, and they know it, and they're out there and they're doing the work, and they're going to be replacing you someday. You know, they're going to have this knowledge before today. And that's my goal, is to teach the next generation about how this works and have them actually do it by farming. And they're having this great time. I have 13 interns this year. I pay them $1,000 a month, you know, for 3 months. And we raise that money by selling the vegetables. And that's where all the money goes that we do raise through the selling for the growth of fruit and vegetables, certified organic berries and grapes and all the works. 24 customers. And I have one other revenue stream, and that is my Soil Forward site, and where you can buy or donate a t-shirt that looks just like this one. In fact, it's the same t-shirt. These are my soil t-shirts. 100% of the profits of this t-shirt go to supporting my student intern program. I've had over 250 paid internships through the sale of fruits and vegetables and these shirts to some degree, mostly fruit and vegetables. And I have them in curvilicious styles or less curvy styles. Go to soilforward.org, won't you? I also have them in Klingon. You might know a Klingon. And I also have them in Vulcan. You probably know who the Klingons are in your life. They need soil too. And you probably know who the Vulcans are in your life. And they need soil too, because we all have to eat. And it's the great unifier. So won't you please go to soilforward.org and consider buying one of these shirts and helping support my program so I can help get this information out to the next generation who need it desperately. So that's kind of where I'm ending up here today. I'd be happy to take your questions. We can go back to other slides, and I hope you learned something.
Thank you so much, James. Really enjoyed your presentation and your wealth of knowledge. I know I will definitely be walking around with a renewed appreciation for the soil I'm walking on.
Yeah, baby.
Yeah. Yeah, we've got a hand up. We've also got some questions. I'm going to start with the question that came through in the chat from Melissa, which is,